Hi, this is my final year project, Deep Learning for Detection of Depression by Combining Audio and Visual Images. This is the flow of my presentation today. Firstly, I will introduce the motivations and objectives of this project, followed by exploring the datasets and techniques used or analyzed. Next, we will go through the architecture and results of the unimodal classifiers and multimodal transformers. And finally, we will end off by comparing the unimodal and multimodal models, identifying some limitations and suggesting some future work. Depression is a common mental disorder that affects approximately 280 million people worldwide. It could cause great suffering and impair one's ability to function daily at work, or even lead to suicide. However, in most cases, symptoms can be improved with early intervention from healthcare professionals. Therefore, it is critical that patients receive the necessary diagnosis and treatments. This project aims to develop deep learning models to classify levels of depression. The main focus is to combine information from audio and video features of clinical interviews to predict depression ratings of the patient. Transformer-based architectures and attention mechanisms are used to identify interactions between different features from audio and video and perform fusion of the multimodal features. The experiments were conducted on 3 datasets. The original dataset is part of the DAIC-WOZ depression database and it is imbalanced as shown in the bar chart here. Thus, sampling was conducted on the original dataset to obtain a more balanced dataset. Subsequently, as each modality may have features that are redundant or irrelevant, removing these features may help to improve learning accuracy as well as reduce computation time. Therefore, feature selection was conducted on the dataset. By extracting and mixing important information from the different modalities, the expected output will encompass a richer representation and have higher performance than predicting based on individual modalities. Multimodal data fusion is generally achieved by these 3 techniques. Early fusion involves fusing multimodal data before the analysis is conducted. This technique requires the synchronization of timestamp of data from different modalities. Late fusion involves separately training independent models and fusing only at the decision-making stage. Rules are used to combine the different models trained. Intermediate fusion involves fusion of data at different stages of model training. The representations of different modalities are fused into a single hidden layer and hence allows the model to learn a joint representation of the modalities. Here is the architecture of the unimodal classifiers. For the audio classifier and visual classifier, a 1D CNN is used to allow the model to learn to extract features from the sequences of observations and to map the internal features to the various levels of depression. The text classifier starts with passing the input through an embedding layer before going through LSTM and fully connected layers. Now we will take a look at the results. As you can see from the results here, the audio classifier overfitted, obtaining a test accuracy of only around 20%. Similar results were obtained for the visual classifier. On the other hand, the text classifier performed well, obtaining a test accuracy of 88%. Now, this is the architecture of the multimodal transformer. To adapt to the less well-represented and less discrete multimodal time series data, this transformer is made up of multiple stacks of pairwise and bidirectional CrossModel Attention blocks. The transformer is used to merge multimodal time series data through a feed-forward fusion process from multiple directional pairwise cross-model transformers. The CrossModel Attention module attends to the cross-modally interactions at the scale of the complete utterances by latently adapting streams from one modality to another via attention. The model performed relatively well. Based on the experiment results, the multimodal transformer performed better than the audio and visual classifiers. However, it was outperformed by the text classifier, and this could be due to various limitations that will be addressed later. The transformer also took the longest time to train. However, the effects of balancing the dataset and performing feature selection were more obvious for the multimodal transformer. So here are some limitations identified. Firstly, models were unable to train on the full set of data without crashing the RAM. Therefore, the data was subsetted and could have excluded data that could be more representative of the participant's depression level. This could thus reduce the accuracy of the models. With a small training data size, Underfitting or overfitting could occur and result in poor performance. This could be a reason as to why the audio and visual unimodal classifiers could not achieve good performance. Additionally, the multimodal transformer could not train for a longer period due to GPU limits. Therefore, there may be a potential that the performance of the multimodal transformer could be further improved. And last but not least, the following are some future works that could be implemented to improve the performance of the models and tackle the limitations previously mentioned. Thank you, and I have come to the end of my presentation. Thank you all for listening.